So the competition I picked was the rock, paper, scissors competition. A little bit about me. I'm a Master of Analytics student at Georgia Tech. I'm currently taking a reinforcement learning course. And I'm also looking for some cool data science internships in the ML and RL space. The game really needs no introduction. I think everyone played some form of this rock, paper, scissors, Rochambeau. Like a really simple playground game. Just to cover the basis, every player has an option to go for the rock, the paper, or scissors. And it's rock, scissors, paper in this infographic somehow strategically. I don't know. So the rock beats scissors, the scissors beats paper, and the paper beats rock. It's pretty circular in that way. Now, how do human beings play rock, paper, scissors? I swear when you search this, you won't get a guy in a suit knocking on your door and flashing your face with a light. This is a legit Google search. Sometimes people say the best strategy is to be truly random. But being a human being, it gets very hard to be truly random. Some people like rock better. Some people like the feeling of, I think I see a comment. You are very much good, Srishti. This is going to be a pretty basic presentation. And back to the topic, human beings are kind of hard to be random. They like a particular, I don't know, action more. They have a little bit of non-randomness. And how about reaction? That's actually another strategy that some people use. My uncle used to always do this to me. He would just look at my hand so intensely. And as soon as I pull my hand from my back and try to go for like a fist, scissors, paper, he would just like suddenly switch. I'm like, what the heck, right? So he would just react faster than me and he would just like beat me every single time. And third is a tells. So it's kind of like these gambling movies where you see your nostril kind of flare a little bit. And it's like, oh, that guy's going for a rock. I think that's kind of the harder one of the three. When I did a search, Esquire.com posted some strategies. So number one, statistically, males tend to be opening with the rock move first. And this is supposed to be a more powerful throw. And as a result, you probably should go for the paper move first. Number two, bluff your opponent. So you tell them, hey, I am going for a rock and I'm going to do rock no matter what. And then you go through with it. You go for the rock. It kind of just psychs some people out and they're like, oh no, is he really going to do a rock? What if he knows I'm going to do the rock? The third strategy is actually to use a throw that would have lost your opponent's last throw. So we actually kind of covered this strategy a little bit in the 1 and 2 step lookup. So people tend to not go for the same one twice in a row, and they like to go for a stronger move than the last one they used. And the fourth one, if in doubt, go with paper. Statistically, it's the least played move, and you could gain a slight advantage, apparently. So this kind of speaks a little bit about the non-randomness of human beings. We do have a little bit of a distribution in us. And now...
Sorry, Stephen. I'm trying to make sense of that last comment. If paper is the least used, that doesn't mean it's the best strategy, right? Don't you want to pick the move that's going to beat the move that's used most often?
Right.
I think when you say least moves, because it's the least popular move, and if the rock is the most popular, taking out, and you take out paper, then you are basically winning every time someone's taking out a rock.
Yeah, that's true, but that relies on the fact that rock is most popular. If scissors was the most popular move, then it wouldn't make sense to go. Well, anyways.
No, I totally agree. That's worded kind of ambiguously. I think it's more useful to know what's most popular than what's the least popular. Yeah, I totally agree there. This competition requires people to submit things called agents. So like, what are they? Do they always wear an eye patch and yell at you in like a, whatchamacallit, what's that guy's name? But you know, like Agents of S.H.I.E.L.D. That's a stupid joke I was trying to make, but that did not fly. So in reinforcement learning, agents are things that make actions, and they're kind of prompted by rewards. So with our agent here in the picture that I stole from Wikipedia, he performs an action on an environment. So this could be any type of game, a mouse running in a maze, a robot performing an action on a maze, or even a robot trying to make rock, paper, scissors decisions. And then this gets to the interpreter. And the interpreter selects a reward and for the agent and also gives the agent a new state. So in our example, the agent will be throwing out a rock, paper, or scissor into the environment. And the interpreter would either reward the agent with a win or a loss here. So, hey, congratulations, you beat the other opponent, or darn, you didn't get him this time. Try again. And the interpreter also gives the agent a state. So the state would be rock versus scissor. You threw out the rock, the other person threw out scissors. Your next prediction, the other agent's next prediction. So that's what we're tasked with creating. This thing that takes in states, takes in words, and spits out the action.
I have a question.
Yes, go for it.
I've heard a lot about RL, and I always get these terms, agent and environment, but I've never understood this in terms of mathematics. Like when we talk about machine learning or anything, we at least can relate with matrices. Okay, this is what matrices are doing. But in terms of reinforcement learning, what is this? Like is it like a probability? Is it like multipliers? I don't understand what's happening at mathematical level. I do understand the intuitive level, I would say.
Maybe it's up for discussion, but from what I understand, it is a list of actions, environments, and states. And that kind of gets combined into rewards. And that's like a temporal cascading game, I would say. But if anybody has a more succinct and better definition, I would love to hear that.
I would, well, I don't really know, but I would assume that the agent can be anything that can execute a function. So it could be a neural network or some collection of code. It takes two inputs and it has one output. So, I think in the context of what we're talking about here, there's going to be some sort of neural network that learns from these interactions that happen.
The agent can be any function. I mean, if that is true, then I really get it. I just didn't understand it in terms of agent. I don't know what agent is while implementing it.
Right.
Like whenever I see a code, I don't know what is the agent in that code. Diagram shows agent. I don't know what in the code is an agent.
Yeah.
I think in this competition, the agent would be the code itself or that function.
Sounds good. And then what would be the environment then?
So in this, the environment would probably be all the moves that were played out. I would think.
That would be all the inputs that are getting into the function.
Actually, in this case, I'm pretty sure the environment is another agent, something else that they're playing against. That's not usually the case, but in this specific example.
Yes, but at the same time, I think the agent itself is also a part of the overall environment too. That the environment supposed to encompass like everything there, pretty much. So it's the rules of the game, it's people who play the game, and the people who play the game, which are agents, interact with the environment itself. So it's playing itself and others.
Sounds good. I mean,
I provided a link in the chat for a good video from a professor at Washington State University. He's an engineering professor, and he gives a good overview of what reinforcement learning is. So if you want to look at that link in the chat there, it's a YouTube video, maybe 20 minutes or so.
Yes, I like the fact that he has a degree and he teaches, so he's definitely going to be explaining it better than me. Yeah, definitely check that link out in case what I'm saying is a bit fuzzy or not clear.
We can obviously discuss it in the end. I just had a quick question.
For sure.
In.
No, this is great. If you have any questions, jump out, raise your hand, unmute yourself. This is great. Okay. So going back to my slides, I'm going to go to the next one. So for this competition, there are a set of evaluations and rules. So a person can submit up to 5 agents a day, and it's actually a Gaussian skill rating. So it's a normal distribution with a mean and a sigma square variance. And the mean itself is meant to represent the skill, the MMR, the ELO, and the sigma is the uncertainty of the estimates. So the initial ELO of these bots would be 600, and they play around 8 matches a day with other bots or agents. And the winner would experience an increased mean for ELO, and the sigma, or the variance of their skill, is adjusted based on the difference of the mean or the skill.
What was ELO again?
Sorry?
What was ELO again?
So it's kind of their skill rating.
It's a chess term. It's something that's used to rate like players of chess. Basically, I can't remember what the scale is, but if you're separated by more than, I think, about 300 ELO, then you'll win close to like 100% of the time against the weaker opponent.
Also, if you're versing somebody that you have a higher rating than, then you'll gain less points by beating them, and you'll lose more points if you lose to them. So it's.
Is this a term from chess itself, or is it like a program, like math term or programmable term?
It is defined mathematically, but it was always defined like the origin of the function was from chess.
Chess. Okay, sounds good.
Mm-hmm. And so the loser would experience a decrease in their skill level, and their sigma it would be adjusted. And so if you can imagine it, if the player with a higher ELO plays a player with a lower ELO, and the player with a higher one loses, then the sigma square would actually increase, because there's a bit more question about whether this person has its true matchmaking rating or ELO, right? But if the other way is around, the higher player wins, and it's like, okay, great. I think we're more certain that this player has a higher skill rating.
So sorry, again, a question. So if ELO is high of some person or the element here, and if the person loses, why will mu increase? Sorry, did you say decrease? If ELO is high, then its skill should increase over time, right? Or will it decrease over time?
So I think it's more like a label. Like, for example, if you are supposed to be really good at the game, but you lose to a person who's not very good, and it's like, oh crap, my existence is in question. Like, am I actually good at the game, right?
So it decreases. The skill decreases.
Yes. So his ELO would decrease, but the variance would actually increase, because you're not sure if this is the right rating for him.
Oh, okay, makes sense.
Okay, awesome. So this is actually played out of 1,000 rounds. So if you're like me and you get kind of tired after 5 rounds, and you just throw like paper the whole time, you're probably not going to do very well in this competition. And also the match scoring does actually not, it doesn't affect the magnitude change in the mu. So you could either win by 999 rounds, or you could win 501 to 499. That doesn't really affect how much the mu changes. The match scoring only affects whether it's a win or a loss. And there's also one other interesting thing. So agents must produce an action in 1 second. I'll open up to the floor. Why do you think that is?
Quick decision?
Yes, but why quick decision?
At least in terms of actual game, so that the other person or the team does not have time to guess what's the next move. That's what I understand in the real world. I don't know what's happening here.
You fell into my trap, especially after giving my example about my uncle just kind of guessing your reaction. I think initially when I saw this, I was like, yeah, totally. That makes sense, right? The other bots should like see what you're doing, kind of like pick apart your strategy and say, okay, this guy's taking a long time. I can see exactly what he's thinking. But upon like a little bit more thought, I don't think that's the case. there are very strict limitations on how much submissions, how many agents one can submit. And if you're thinking about it, with up to 5 agents a day, with 8 matches a day, up 1,000 rounds, that gets pretty expensive computationally. And if you keep on just submitting agents that just keeps on going, and that all take over 1 second to make a decision, it's going to be very clumped up. And if you have more time, it's going to be pretty tough for the back end stuff.
I think the other reason for it is they also want to limit they probably want to limit users from just submitting huge ensemble models that were just like a combination of the best agents they could find. So like,
but how does that prevent this limitation? Like, even if in an ensemble model, can't that agent actually still produce an action in 1 second?
If it's too large an ensemble model, then it's going to take longer than that to actually run the model.
Oh, okay, right. Okay.
Like in this case, it's probably not as much of a concern. But if you're talking about like image processing or an NLP, then it's quite common for predictions to sometimes take an hour or something like that for larger models.
This brings me to another question. If it is expecting an action in 1 second, then anything which is like any model will take more than 1 second to make a prediction. I assume it will take some time to make a prediction or some time to learn.
I think we'll explore the different types of models a bit down the line. And like the ensembling model, I think that does come up. And now that you talk about it, I do see where that come into play with some of the solutions. Like, for example, people seem to be pretty hard capped at using 50 other agents in their modeling. So I think that might be also a key factor in the 1 second goal too.
Hey, Stephen, just to clarify, can you just go back? So the agent that you submit is playing against the agents that other people are submitting. Is that right? And there's 8 matches a day, and a match is 1,000 rounds? Mm-hmm. Okay, so you're up against 8 matches a day. Okay, so you're up against a maximum of 8 or approximately 8 other competitors in the competition each day. And then you get presumably random matchup. Well, is it random matchups actually?
No, actually, it's not. It's based on your elo.
Okay. Cool. How many teams entered this?
I think last I saw 1,500 teams.
Cool. Okay.
Yeah. So more than 1 second could really hinder.
Yeah, that's another reason to limit to 1 second. Yeah.
So my initial thought was, if we have a random agent, or if we have an agent that is fixed and predicts like only rock or something like that, probably should win 1/3 of the time, right? I mean, that's 1/3 of the thing you can throw, right? It has to win against something. But it turns out random agents or fixed agents aren't very good. For example, one person was looking to do the worst model possible, and he did submit the rock. And it's not the worst. Like, by far, it's not the worst. The only rock model actually got an elo of 371 points. And we start at 600. So that it's losing more than it's winning, but it's still not like the rock bottom. It's throwing rock bottom. But yeah, so there's got to be some strategy or some mind play here going on. And looking at analysis of the top solutions that I actually posted, here's a small Excel spreadsheet that I took down. For the first place, they've used the pattern recognition 1, 2, and 3-step looker. They use something called inverse agents or anti-bots. And third, they use rock, paper, scissors competition agents. So that's an external competition. And they did not use a technique called drop switching. They did not use something called initial randomness, but they did use something called a multi-armed bandit. So that's kind of a think it's a pretty common model that's used in reinforcement learning. So next we'll go through piece by piece on what these sections are. Pattern recognition, and I have a fun task. The next couple of slides are extremely bright. They're like yellow, so I'm sorry if they destroy your eyes. It's going to be 3 quick pattern recognition tasks they should be simple, medium, complex. And if you see the pattern, just feel free to yell. Ready? Okay. So this is our first pattern. If you see the pattern, feel free to unmute yourself, yell it out.
Rock, scissors, paper, rock, scissors, paper.
Awesome, you got it. I have a great audience here. This is great.
Stephen, what is? Are we supposed to be reading these left to right, or how do we read
It's a
these?
pattern. You have to find out which pattern.
It's a pattern.
Doesn't matter? Okay.
Yeah, just feel free to yell it out as soon as you see it. This is kind of like a allusion to the things that are going to come up later, but with this, I think when I initially assembled this, it was from left to right, left to right, left to right. So now level 2, now that we got the first one. A little bit harder, right? But this was actually similar to one of the things that people use. Okay, I have one challenge. If it's Chinese, read the bottom, right to left.
I think it's.
I like how you actually broke it up too, just to match this kind of broken and cringly version. So let's give it 10 more seconds if anybody comes up with an answer.
I think it's rock, scissor, paper, then double rock, scissor, paper, scissor, then it starts again.
Is it? Let's see.
Oh no, wait, it
There's
doesn't.
2 papers.
It does double paper after that, right? Okay.
Okay.
First 3 rows are identical along the diagonals. Scissor,
Yeah.
scissor.
So the pattern is repeating.
Yeah.
There is a pattern. I guarantee that there is a pattern. It's not like randomly generated. And there probably are more than one pattern in there that I did not kind of think about when I generated this.
I think it's just a bit longer than it was before. Like, so it
Yeah.
seems to repeat after the 2 hands.
Yeah. After the 2 hands. Second row, first rock. That's when it starts repeating. That's why you see the diagonal pattern.
Yep.
At least in the first 2 rows.
But then the pattern breaks in the last 2 rows.
That's just because of the way that it's ordered, though.
Yeah, Stephen, you're really messing us up with the way that you've changed the width of these rows. What are we not getting it, Stephen? Why are you
Okay. So the pattern here is so it's rock, scissors, paper, rock, then rock, paper, scissors, rock, scissors, paper, and then it's scissors, rock, scissors, paper, and then it's paper, rock, scissors, paper.
It alternates. The first thing always alternates.
Yeah, so the first thing always alternates between rock, scissors, and paper. And then you have 3 chunks. And this kind of break in the pattern is really to just mimic the conditions of our intense competition, that they kind of switch it up or they do have a delay sometimes. Okay, are we ready for the intense expert level?
Shoot.
I'm getting no responses, so I'm going to assume that is yes. So this is our 3rd level here. And we could go for a minute. And if you see anything, feel free to shout out.
It's like the scissors and the rock. They're swapping.
What do you mean by?
Yeah,
If you, on top on the zoom little bar there, if you click more, you could try annotating what you think the pattern is.
thank you.
Oh, cool. We've never used that feature. I don't think it never repeats, right? Because those first 4.
It's something like a Fibonacci sequence where it takes the previous 2 values and then bases it on those.
That's not how I generated this, but let's see would that make sense in this pattern.
I'm not sure. Because like scissor rock always seems to be followed by scissor, and then rock scissor is always followed by paper. I guess that's not actually always true.
It might be what we're seeing from this sample here. Right. So
No, it's not.
I just found a counterexample to my. Example, so it's not true.
Okay, gotcha. So that we don't sit here for the entire session thinking about this. So how I generated this is actually the first 2 columns are completely random, and everything else follows a predictable pattern. And you're thinking that's kind of unfair, right? Like, what the hell? You're using random stuff in the pattern? That's stupid. Like, you're trying to trick us. But this is actually one of the patterns that one of the agent was similar to one of the patterns that agent would have generated. It's in the same spirit of thing. So, and this is actually something that one of the agents kind of semi-picked up to playing against it. So although this feels really unfair, our models can actually kind of suss this out and try picking it up. Yeah, so the first 2 are just complete BS, and everything else is. This isn't some of this a double like Tim Hortons? A very Canadian reference. I like that. Makes me feel proud to be Canadian. So yeah, this is the pattern.
I'm not Canadian, so I don't get it.
When people get 2 pumps of sugar and 2 pumps of cream in their coffee, we call it double.
Okay.
Yeah, I don't think that's a thing anyone else.
Because the coffee is so bad.
It's really watery, yeah.
I used to work at Tim Hortons.
In the one I went to in Shanghai, apparently they don't do double either. So I think it's mostly a Canadian thing. It's not a Tim Hortons thing.
So David's pattern was actually right. It's just that the first 2 columns you created were random.
Yes. So congratulations, you're almost there to be a reinforcement learning model. It's like, I want to be a reinforcement learning model.
That'd be a bit slow.
Don't worry, you're plenty fast. Moving on to our first, second, and third step looker. So that's where the kind of the random pops up. This kind of strategy looks at the opponent's last moves, and it makes just moves and predictions based off of that. For example, if the opponent comes up with a rock, paper, scissors, that's their kind of lineup for the first 5 moves. If you're using a first or one step looker, your first move would be random because that's completely empty. You have no idea what their move before their first move is. And the second move is supposed to beat their first move. So you have a paper beating the rock. And the move after that, you have the scissors beating the paper. Then you have the rock beating the scissors beating paper. You kind of get the idea. And the second and third step lookers are kind of in the same vein, where the first 2 or 3 are random, and then you try to beat the hand a couple steps before that. Bruce, you look kind of like angry. It's probably because you think like, this strategy would never freaking work. Like, all these are wrong. They don't win that much, right? And that is partially true. These individual strategies alone, I don't think they would win that much, especially by itself. It would probably be the worst bot ever. And it's going to get eaten up by the boss that we see a bit later. And what's required for the strategy really is the opponent's past history. So you got to have like a notebook and pen, just slowly jotting down what they have already put out. How do I beat their last move, last move, last move? Now, this kind of brings up a iocane powder problem. If anybody has heard of iocane powder, this doesn't exist in real life. It comes from the movie The Princess Bride. So it's when Jack is facing the Sicilian, and there's a problem of two like drinks, and one of them has a quote unquote iocane powder in it, and it's supposed to be a severe poison. And the Sicilian keeps on guessing. So I would put the poison in my cup, which means you would have switched the cups, but you would know that I would put the poison in my cup, so you would switch the cups back, and it keeps on going back and forth to infinity. And at the end, you don't really know what's happening. So the rationale is that if I know exactly the strategy that my opponent plays, it should be kind of easy for me to counter them in my next move, right? I could predict the same way that they predicted. What if they know that I'm thinking the same? And I know that they know, and they know that I know that they know. And it goes in that infinity. This is actually a strategy that's employed by Stas C. He's actually ranked third, winning 95% of the games at one point in the competition, until people started catching on to his anti-bot strategy. So for this to work, you need to know the opponent's past history, your own history, and knowing what the opponent's strategy is. So you have to know their kind of meta knowledge. Like, for example, if I know the opponent has a one-step looker, then I could predict them pretty much exactly. But the iocane problem is just, the iocane powder problem just comes with like, oh my gosh, I need to know so many things. And so let's give a quick example of countering the 1, 2, 3-step looker. So to counter the one-step looker, the first one's random because you can't really counter random. That'd be pretty hard. And to counter the paper, you go for the scissors. And to counter the scissors here, you go for the rock. And to counter
Stephen, sorry to interrupt. Is it just me? You're going through periods where your audio is getting very low.
Oh, sorry.
Yeah,
I have that as well.
Oh, can you hear me better? I don't know where I cut out. Sorry.
Yeah, I think if you sit a little closer to the mic, you'll be better.
Okay.
There's also an icon coming up in the bottom left of the screen when your mic cuts out. So I'm not sure if it seems correlated.
Oh. Is it icon?
Yeah, that icon.
With the pattern recognition.
Maybe it's unrelated. I could be forming false patterns in my brain. Anyway.
It looks like a slide thing. So maybe every time
that just looks like a slide counter to me.
Yeah, it's kind of a weird thing there. But I was saying, let's do a quick example of how do we counter the 1, 2, and 3-step looker. So to counter the 1-step, the initial one is random because we can't really counter random. The second step, we use scissors to counter the paper. We use a rock to counter the scissors, and kind of so on. You see the pattern there. And that works with the C2 and C3. So C2 counters step 2 there, and C3 counters the 3-step there.
Okay, sorry. So the context here is that we know our own moves. So we can predict, like, if they are going to use the 1-step looker on us, then we can therefore know what they're going to be playing on us because we know what we had played. And then we're going to counter what that move is. That's what you're saying, right?
Yes.
Okay.
But here, isn't this assumption that the other, how do you say, agent? No, I don't know. Whoever the other party is will be actually using the 1, 3-step looker every time for you to actually counter that. So is this assumption true? Like, do they assume that every time person will be using a 1 to 3-step looker?
So with this strategy, there is definitely going to be a bit of misclassification of the models. So yeah, like if I think they're using a 1-step looker, but they're using a 2-step looker, I might be pretty screwed using just this strategy.
Yeah.
But the beauty of having these strategies is that at the end with the multi-armed bandit, it kind of does a bit of an ensembling, but with a little bit of randomness mixed in there. Yeah, definitely hold on to that question. I can talk more about it in a bit. So does the counter work? that makes sense in one side.
Yeah, I'm curious why we stopped at 3-step lookers. Like, couldn't you just keep going up to more?
I think that was a
more?
question that I put down after, where yes, do we need a counter 4 times? So do we need a counter 4 times? That's open to the. So the quick answer.
So if you counter 4 times, then that just brings you back. Hold on. If you counter like 3 times, doesn't that just bring you back to the beginning?
That brings you to exactly what the other player put down.
Yeah. So like a 4-layer counter is just the same as a 1-layer counter.
Exactly.
Sorry, I'm not asking about countering 4 times. I'm asking about looking back 4 times.
Whether you can have a 4-step looker.
Definitely. You could definitely have a 4-step looker. Yeah.
Okay.
Yeah, it's not limited to 3. And because we have 1,000 games, I think you could even have like 1,000 minus 1 step counter. Although it doesn't become very useful if you lose like 90%, 99% of your games, you win the last one, and you kind of know the pattern there. Yeah, and by that point, you probably are just tossing it up a chance if by the 1,000th move you're countering the first move. Okay, and we answer his question. Do we need a 4-layer counter? We don't need it. So yeah, you could probably see that all the other counters collapse into the first 3 counters. And now we have the external agents, the strategy theft. The rationale is that if there's another competition that has like public and proven bots, why do I really need my own strategy? I don't need to program it from scratch, right? So this is actually a very popular strategy among the top of the leaderboard, at least partially. So there's another competition called the rock, paper, scissors programming competition. Very similar name. I wonder what they do. This is empirically actually used very widely, as I said, and the requirement for this strategy is that it needs other well-performing bots or agents. If there's nothing else external, then you can't really use them. And some of the top solutions from rock, paper, scissors competition are shown here, like IO2 fighting you. No idea what that's supposed to be, but there are some strategies there. And all these codes are actually open source. So you could just find them like laid out like that as soon as you click it. I tried clicking the human versus computer here, but the URL is somehow broken for all the strategies. You could definitely try giving it a try if you see them.
Stephen? Sorry, I wonder if you should try turning off the automatically adjust the microphone volume feature.
Ooh, yes.
Oh, that's a great idea.
Yeah, maybe that'll help.
I was testing your theory, Dan, and it was not popping up at the right time. So.
Yeah, I was wrong. Sorry about that. Maybe I'm
audio settings?
Yeah, in the audio settings, if you go to test your...
It's actually off.
Okay.
Well, maybe put it on.
Yeah, maybe I should turn it on.
Could try it. Yeah, something's causing you to cut out. It was good for a while, then it started relapsing again. Don't know.
You know what? I can put headphones on. That's probably better.
That would probably work
You
really
have a
well.
mic.
It's probably a bad echo cancellation going on or something.
Oh, there you go. Look at that.
Okay, can you hear me better?
So far, so good.
Great.
Okay, I could hear you better. It must work the other way around. But yeah, so these guys have public source code with like a lot of games played. Some people played like 696 matches. Sorry, you can't hear me anymore? Or
No,
it's happening again. That is so
you
weird.
Change, like sometimes you have to actually go into the sound settings and then change the audio source when you change.
Yeah, your mic not be being used right now.
Oh, it's not used. Okay.
Maybe it's just me, but I can hear him every time.
Oh, it doesn't get loud and quiet for you?
Not. I mean, I don't think it was anytime so low that I could not hear or had difficulty hearing. I was able to hear him every time.
It's the same I think it's the same for all of us. We could still make them out, which is good. So it's not like you need to repeat anything, Stephen, but it was a little suboptimal, I feel.
Okay, yeah, sorry about that. I don't really know what's going on, but if it's okay with you guys, I'll just continue with the slides.
Sure.
Okay. I was just saying that there's a lot of matches played here. So it's already pretty tested, tried and tested agents, and they seem to return pretty good predictions. So as we saw from the fifth slide, probably, with a little Excel junky spreadsheet, a lot of teams or a lot of groups that use this external source. I don't think they would have. Is the sound getting worse for you now that I have headphones on?
No.
So far, has been stable.
Okay.
At least for me.
Okay. Yeah, it's super weird. Doesn't look like we have a solution. Yeah, all the source code is available, and this human versus computer, that doesn't work. Now we're going into the kind of cutting my own limb off so that I could hit people with it strategy. So the two are drop switching and initial randomness. The drop switching rationale is that I've already lost so many freaking games already with my strategy. Let's just abandon all of that because it's going to lose anyways. Let me just go drastic and go 100% random. This way it would actually give me a semi-fighting chance. But empirically, that doesn't actually work too well. Only the 7th or 6th place solution use this strategy. There's also the initial randomness, which is, let me confuse the crap out of you with my first 100 games played against you. Pure random. I'll give you a lot of noise so that your model picks it up. And as a result of that noise, you probably won't beat my future moves that well. And this wasn't actually very widely used, but it was used by one team. And now we have kind of the consolidation step. We have a lot of strategies, and individually, they're all super duper weak. Like there is pretty obvious flaws to each one of them. But with our multi-armed bandit model, there's multiple agents with different strategies. And we generate a random number from this distribution, which gets updated every time a match gets played out.
Can I ask a question here?
Yeah.
What is multi-agent here right now? Oh, like again, I'm back to the same question when I talk about agents. Like, what does it mean multi-agent?
So here, I think I'm more referring to the strategies. We have a lot of different strategies.
Oh, okay.
So there's like the one-step looker, and then there's two-step looker, and the three-step looker, and there's the two-step counter, all of those sorts of things. So basically,
like ensemble, which you mentioned previously.
Sort of. In this case, like the multi-armed bandits, like you can probably explain this just as well as I can, Stephen. But it basically refers to like you try one, and then you see how well it does, and then you try something else. And like the probability of choosing any given strategy is dependent on the past performance of those strategies.
Oh, okay, makes sense.
Mm-hmm. And I should walk through a quick little, quick couple iterations to show you how that works. So the distribution is a beta distribution. So continuous, initially from 0 to 1. And A is the number of historical wins of this agent, and B is the number of this agent's historical losses. I think when I typed it, I actually flipped around. This would make sense. So it'll be beta of B plus 1 and then A plus 1. And each time we select agents with the highest number that's picked from this distribution. And it's kind of a mix between exploring what works and also finding out the opponent's strategy. And I think the next couple of slides are just me talking through. Let's talk through a couple iterations of this, just so we get our head around it. So initially, we have 3 agents: Corgi agent, Duck agent, and Panda agent. I promise you that's a panda. That's not a circle and a random body. It's the background of my slides.
It kind of looks like a ghost when it's the black background.
Sure. Ghost agent. That sounds much cooler. Sci-fi. So through our corgi agent, we predict paper. Through our duck agent, we predict paper as well. And through our panda or ghost agent, we predict rock. And our initial distribution is B01, B01, B01. And we pick a random number from that distribution. And from these numbers, we find that, hey, duck agent has the highest number out of that distribution, has 0.78. And so what our multi-arm bandit would propose is, let's go with 0.78. That's as good number or as good move as any. This is our initial move. And our opponent throws out a rock. So, oh my gosh, we lucked it out. We won that one. And as a result, the winning agent would have their distributions changed. So the corgi and the duck, they would have a B of 0 and 2. The losing agent, sorry, ghost agent, you're stuck predicting ones for now. And now our second match out of the 1,000 matches. Here's our new updated distribution. And our corgi agent predicts 1.5. Our duck agent predicts 1.2. And our ghost agent, sorry, you're stuck with 1. And based on these numbers, we actually select rock because we got the highest number drawn from that distribution. And our opponent plays paper this time. So bad boy, you lost. And the corgi's distribution goes from 1 to 2. The duck goes from 0 to 3, since technically his prediction won. And the panda stays because it's a draw then. So does that kind of make sense from how we select the optimal strategy? Sorry, it looks like I'm losing everyone here. Are there any questions?
It makes sense. I just feel like the rock should be still 0-1 at this game too.
It was updated in the first game. So this gets held on the distributions. If that makes sense.
But
so initially it
actually
won.
Oh, it went paper. Oh, I see.
So they both predicted paper here.
Oh, I see. Never mind.
And so even with what they predicted does not get used against the opponent, they still kind of have a tally of if they won historically. And so in game 2, we select based off this distribution too. It just that the more your model or strategy loses, the more unlikely that model or strategy gets selected into our model. And it's less likely to be used against the other opponent. And even though there is like a likelihood happening here, a probability happening here, we could still draw like zeros from both a duck and corgi agent. That's not a possibility, right? So panda still comes up, but it's a very slim probability. That it only predicts 1. Right, okay, awesome. So that kind of shows how people would combine these strategies together. And this was a strategy that was used by the first and second place there. And so, yeah, that's what I talked about just a couple of seconds ago. Based on the updating here, the corgi goes to B12, duck 03, and panda 11 still. And as an agent wins, the chance of getting selected increases, and if they lose, they're less likely to be selected. I don't think I have any more slides after this, so I hopefully this is a good walkthrough of these competitions. If you have any questions, wanted to flip back the slides, feel free to tell me now.
I've got a question, Steven.
Yeah.
Near the beginning, you explained that if you have an agent that only ever predicts rock, then he's actually not the worst agent that's out there. Can you describe to me who is losing to this agent that only ever predicts rock? Like, what sort of strategy would you have to have? Maybe an agent that only ever predicts scissors, I guess, would lose, but like...
a random strategy might also lose to it.
Yeah, actually. But...
Well, a third of the time they would lose, a third of the time they would win, and then a third of the time they would draw. So, like, if depending on the distribution, like how many scissors you end up with, you might end up losing.
a random strategy would be 600 ELO. Is that right? Like it would just stay the same in the long running average?
I don't think so. I think 600 ELO is just the number that you start at. It's not the number that you that reflects any particular strategy. It's just like, this is your base level. You're assumed to be this good to begin with until proven otherwise.
But wouldn't it just eventually it would never be able to improve, or like
it could get worse
if it went to infinity?
Yeah, I do think it could get worse though, right? Because that's just an arbitrary number. It's it could definitely be squashed down if you have a lot of people submitting better strategies than random. Or
if a purely random agent played 1 million games versus any other agent, it would be winning half the time and losing half the time, wouldn't it?
Yes, but it matters what type of ELO the opponents have. So the order of which they are won, I guess, matters. Because initially the agent will be playing against 600 ELOs, and if they lose or win the next one, it depends on what the opponent's ELO is.
Right, yeah, I get that. But irregardless of the opponent's ELO, they're going to be winning half the time and losing half the time. So I think, anyways, I can't quite wrap my head around this. I want to come back to the rock question. Who can you tell me an agent that's worse than rock only?
Well, besides the answer of a very unlucky agent, so predict what it will predict scissors more than half the time is what we're trying to say, right?
So if something cycles between scissors, paper, and rock, then like it's not going to get through a complete cycle by the time it ends 1,000 rounds. And if your starting point was scissors, or if the second one was scissors, I think. No, sorry. If your starting point was scissors, then you'll end up losing, I think, 334 games out of the 1,000, and you'll win 333. So you would lose against the rock strategy. So like anything systemic anything that was systematic and rotating between them would lose to that strategy if it's happened to start on scissors, for instance.
All right, I feel like, no offense, Dave, I don't feel like this is taking us anywhere super interesting. I want to keep brainstorming with you and playing around with this, but let's maybe see if anybody else has some questions and we can talk about this more after.
I had one question. On slide number 23, where you were going for game 2 in the simulation. Yeah, here. So here, when our selection is rock and opponent is paper, it means paper won because the rock lost. Shouldn't pandas be, I don't know, 1, 2 or 2, 1? Why is panda still 1, 1? It's actually, it won the simulation, right? It should have an increment if I'm getting it right.
So what we control is we control what the top portion of it. Where's my annotates thing?
So Panda wouldn't have won this one, right? Because it's paper versus paper.
Panda would have tied. So Panda predicted paper, and our opponent came out with a paper. We just didn't select.
No, like in game 2, our selection was rock, and opponent went paper. So whoever, maybe I'm getting it wrong, but I thought with the initial calculation, it had an increment on either side, like B plus 1, A plus 1. Mm-hmm. So if somebody lost, it shouldn't it be B? If I'm right, it shouldn't be B 2, 1 because it lost.
Mm-hmm. But paper actually tied with the opponent, so it didn't get an increase or a decrease. So Agent Panda predicted paper, and our opponent threw out a paper too.
Oh, so in case of if the prediction is similar to what the opponent makes, and there is no increment.
So it's like when you play rock, paper, scissors with your friend, right? Like if you keep on throwing rocks, you just keep on going at it again. I don't know if that's everywhere in the world, but
it happens a lot with people who know each other. So if you know the person you're playing against, it, then the most likely outcome is that you end up throwing the same thing over and over again.
Mm-hmm.
Like not necessarily even the same move, but like you might both go rock, and then you might both go paper, and then you might both go scissors.
So does that make sense why we didn't update this distribution?
Yes, but then if you go to game 3, the next slide.
Mm-hmm. Yeah.
Is that right? Yeah. What happens to is it still continuation of the same game, which we have been talking the past 2 slides?
Yeah, so it's the same game. It just their distributions have changed, but I didn't put their predictions up.
Okay, makes sense. Okay,
Yeah, so this is the continuation of the ones here. And, so yeah, as more strategies win out, the more likely that they'll be selected for our kind of grand action, I guess. And yeah, I think there are probably a couple of applications for this, I guess, but they would have to be you have to be repeated a lot of times, right? If you're using multi-arm bandit, this has to be quite a couple of games for it to learn from, see who won or lucked out. Because if you're doing 3 games, for example, it's not very true to say that the AI would win. You completely luck out based on this distributions, or the number you draw from the distributions.
So I had a question at this point. Was this as complicated as the algorithms got? Because I can imagine doing things that are considerably more complicated, like where you have a bank of strategies and then you try to figure out which one your opponent's using, and then you try to like based on that you try to like employ the strategy that beats the strategy that they're using. So you have some kind of like a I don't know.
Well, in a way, this is a bank of strategies.
It is, but it's probability based as opposed to
like solidly, I know exactly what you're doing.
Yeah, so like you could have an algorithm which predicts which is essentially a classifier, and it says like it predicts a probability of the opponent using a particular strategy, right? So like the outputs of that algorithm would be, one looker or two looker or two looker counter or any of the other examples, and it would like predicts like a soft, and then it would apply like a soft max to each of the predictions so that you get one prediction for which algorithm your opponent's using, and then you just routinely use a strategy that beats that.
Mm-hmm. So I think that would require like a really good understanding of what the meta is or what the strategies are in each person's like arsenal.
Yeah, but I mean, I feel like that's probably not actually that difficult to achieve given like the strategies that people employed.
Oh wait, I'm sorry. I wasn't really phrasing myself right. That's actually one of the anti-bots or anti-strategies they have. Basically, they made inverses of each of the strategies they themselves have. What it reminds me of kind of like Hearthstone, where you have these meta decks, right? And you kind of like, okay, since he's running a ice mage deck, I know what he has in his hands. The white.
Yeah,
so but I mean, inverse agents.
You could have, for instance, an algorithm which knew all of these strategies, right? And then, like, the first thing that it did was try to predict which one the opponent was using. At every move that the algorithm made, it started by predicting, okay, what's the probability this person is using X, right?
What's the probability this person's using X? But that would. So initially, I'm thinking is that like they would have like very even distribution of all the strategies, and then the probabilities get updated every time a new match is revealed. And basically, what you're saying is that it's better than doing like a probability based, but rather like a hard clamp saying, like, I know exactly what you're using.
I think so. I mean, like maybe this wouldn't work because I wasn't in this competition. I didn't try it, but that's one of the first places that my mind goes when, especially when you have some idea of all the strategies that everyone else is using.
Gotcha. Okay. So, but what happens when it faces like a multi-armed bandit like this, and it gets another distribution, right?
Yeah. So that's a little bit more difficult. But so I guess the ideal situation is that you're continuously winning against the multi-armed bandit, in which case you know which strategy, like in which case the strategy is sort of random to a certain extent, right?
Mm-hmm. Actually, I think it was one of the design philosophies of, I think, number 2, the top 2 person. He was saying it needs to be effective, but it also needs to be stealthy in a way that they cannot figure out what I'm doing at the same time.
Mm-hmm.
Oh, what does bandit mean? Is it strategy? I think the bandit kind of comes in the fact that like it steals people's strategies. No, not at all.
The history behind this is that like poker machines, the ones that they have like the arm that you pull down and then it spins the wheels.
Mm-hmm.
Yeah, so those are called one-armed bandits.
Okay, they steal your money.
Yeah, because they steal your money. So basically, the idea behind like a multi-armed bandit is, let's say you had lots of those machines in a row, like which one, like, and some of them actually like have a higher probability of giving you a payout than others. This is how you go about figuring out which one you should be playing. So you need to explore enough of them so that you have some idea of which ones are likely to win, but you need to you really want to focus in on the one that's actually going to give you more of a payout, if it is. So that's the history behind the term.
Thank you, David. I think we have another question in the comment too. Just wondering, given the best bot and 1,000 tries of RPS, what percentage of throws did it win? So that would depend on which agent it plays. And that's actually not data that I have access to. Everything I have on these slides are just from top solutions that posted on discussions. That is very interesting, though. I think at the end of the competition, where ELO's kind of sedimented and kind of figured itself out, I wonder what the win rates are too.
I think you told somewhere that the best bot won 85 or 95% of all the games.
95% of games, but that's different from the number of matches. They could have won each of those games by like 501 versus 499, for instance.
I think, yeah.
And timing really matters here too, because people start figuring things out step by step and then counter each other. So at that point in the game where like anti-bots were just figured out, like how do I counter the most meta strategies, that guy won 95% of the games. He was just steamrolling everyone, except maybe the rock bot that just predicted rock. All right, so do we have...
R has a question in the chat. Do you see that? Or do you want me to read it out?
That's one we just kind of talked about, I think. 1,000 tries of rock crystals.
Okay.
Okay. If there's any more questions, we can take them at the very end. Stephen, this is great. Lots of really interesting discussion. I was a little skeptical going in, rock, paper, scissors, how interesting can that be? But oh man,
there can't be strategy in here.
That was awesome. I love that. So interesting to think about. So thank you so much for walking us through that. If I can get everybody to unmute themselves, and we're going to give Stephen a round of applause to thank him for the presentation. And I'll count us down in 5, 4, 3, 2, 1. Oh yeah, you can do this as well.
Thank you.
Thank you, Stephen.